Well, here we are. It's Lewis dot electron diagram time again, and we're dealing with ozone, O3. About 1840 is when it got its name. The telegraph was being evolved. Chemists were making batteries that could produce sparks. And if you get a significant number of sparks around in air, in oxygen, you're going to generate some ozone. And the word ozone means smelly. Sometimes if you're around some electrical devices that are sparking and so forth, you'll sort of smell a pungent odor. That's the ozone. It's, like I say, it's unstable. If you have a jar of it, pure ozone, within about 24 hours, half of it will be gone, changed back into oxygen, and that'll keep on happening. So after 2 days, you've got a quarter of a bottle, and 3 days, an eighth. So ozone's got to constantly be regenerated if you are going to have any of it around. If anybody's going to be working with ozone, they basically have to have an ozone generator, which involves a couple of capacitors and sparks and such. But let's get to the Lewis dot diagram of this smelly ozone, O3. So let's see. Valence electrons. Oh, I didn't highlight oxygen here. Let me get my little highlighter out and highlighter. Here it is. Here's my oxygen, and it could have been sulfur too, or strontium. 6 valence electrons. That's where I got this 6 from. And 3 ozones times 6 is 18 electrons. That's what we've got to play with. The drawing the structure is sort of weird. I only got 3 things. Yeah, line them up and designate this character as our central atom. That's going to deal with 18 valence electrons. And once we've got them lined up, we bond them. We stick them together with our little shared pairs of electrons, which are lines. Only 2 lines here, so that's 2 electrons for each line. That means we've got 14 electrons left. Next rule is we take the electrons that are left and start putting them on the surrounding atoms, which in this case is these 2 outside oxygens. And there we go. I've drawn them all in already. 2, 4, 6, 8, 10, 12, or 6 and 6 is 12. That leaves us 2 leftover electrons, which will go into our designated center oxygen. So let's drag it over, and there we go. We've got all the electrons taken care of. I got rid of the valence electrons here, and this would be our ozone molecule, but something is amiss. All is not right in our central atom because it doesn't have that low potential energy octet. And to get that, you can end up dragging a pair of electrons over. As I said before, one of the important things when you do this is to make sure that you don't leave the electrons there. It's easy for me to use this diagram and just move that pair of electrons over. But when you draw 2 in, you're going to have to erase or cross out that pair. Now, I did that there. And again, I could have just as easily and identically dragged it over here. Now, let's double check, make sure everybody's got their octets, which would have been, this is what we need. I mean, we don't have any hydrogen here, so it's octet time. Let me get my little shape drawer here and put in a little circle and check out this oxygen, 2, 4, 6, 8. Yeah, very good, sehr good. Oops, let me get rid of that. Now let's drag my little circle over. Do we have 8 here? Yes, but without the double bond. And how about our central atom? Is it at a nice low potential energy? I could have said, is it happy? But when we're dealing with FRQs, we don't use that term. We'll just say low potential energy because that's stable. Let me count. 2, 4, 6, 8. Okay, we're fine. We've got everybody with their octets. We've got as stable of a molecule as we're going to get. But don't forget, I could have dragged that thing out at 2 different places. So if I'm going to do a complete drawing of this, of all the possible arrangements that would be stable. Oops, let me get back here to my switcherooner here. I should include both of them because both do sort of exist simultaneously, and this double bond averages itself over. So you don't have one short bond and one long. We've got two intermediates because we've got this pi bond. Oh yeah, let me identify the bonds too. I think that's worth doing again. We've got our second bond, which is our pi bond. We have this pi bond, which ends up being distributed across, and of course we have our initial sigma bond, which we put in first. And here we go. There. So in this molecule, we're going to end up having, I think I've got it here. Our central atom has three domains in it. It's got a 1 sigma, a unshared pair of electrons, and another sigma. We don't count this pi bond when we talk about domains because that pi bond really goes up and down, doesn't determine geometry. So there we go. This is a little bit different. Again, we had something we had resonance, we had the same atoms all the way across, but this is the Lewis dot diagram of ozone. You could do a Lewis dot diagram for oxygen, but there's a problem with that. Our Lewis dot diagram, which I rave about all the time, is nice, but it's got a flaw in terms of dealing with oxygen. It does have its weak spots, but we're not going to deal with that now. So, okay, there we go. Lewis dot diagram of smelly ozone.